and welcome to Lessons in Logic video number 43. And before we begin, same valley as last time, slightly different angle, looking a little further counterclockwise, so a little further north, a little less east, perhaps, unless we were already north enough, in which case maybe we've turned slightly west. It feels like we're slightly west. Anyway, we're on Tai Mo Shan, Hong Kong's tallest mountain, looking out over one of the New Territories valleys of Hong Kong. The furthest hills and cityscape would be Shenzhen in mainland China. Tai Mo Shan is a lovely, lovely mountain, and I'm not really sure what else to say about this picture except, golly, I like a good hike on a mountain. All right, so let's go to proofing, and specifically, let's do some basic practice with proofing. Some, not all, but some of you out there are maybe doing okay with proofing and maybe you're not. But either way, some of you need some practice, some slower practice with the basics. That's what this video is for. This is another slow practice with the basics of proofing video. And first we'll do some practice with inference and equivalence rules. So really simple, and my advice is for most of you, at least if you have any need for slowing down and reviewing the basics here, for most of you, if you need any help with that, pause and don't let me tell you the answer until you've checked to see if you can find it for yourself. So for this proof, we may need only one. Yes, it looks like we need only one step. We can go straight to the conclusion. And we want to look for a preceding step that fits the double negation pattern. Two steps to get to the conclusion. We look for a preceding step that fits the double negation pattern. And then we need to look for two steps that fit the modus tollens pattern. So I mentioned last time you could apply double negation to any part of any part of a premise. Like you could go from this premise, if A, then not Q, to if not A, then not Q. My advice is don't do that. Look for something else. If you're following the Beatty rule, but we're working backwards, Mike Beatty's advice from Baylor University, look for a way of getting to this conclusion from the premises. And what you're going to do is a modus tollens step on line 1 to get to this conclusion, which means you're going to need to deny the consequence of line 1, which is to say you're going to need to say tilde tilde Q, which gets us to a double negation step. So here's the solution. You apply double negation to line 2, and that fits the double negation pattern. P, therefore, tilde tilde P. Double negation on line 2 gives you tilde tilde Q. And then the conclusion is going to be a simple modus tollens on lines 1 and 3. Modus tollens is if P then Q, not Q, therefore not P. And in this pattern, if P then Q, not Q, therefore not P, I better type it. Modus tollens is the modus tollens pattern is if P then Q, not Q, therefore not P, where P and Q are lowercase and italicized, meaning they can stand for any proposition you like. Lowercase q and uppercase Q are not the same thing. Lowercase q is a generic symbol for any proposition we like. Uppercase Q is a symbol for a very specific statement in a very specific argument that was symbolized to get us to this point. So tilde Q, capitalized, is actually what we're symbolizing as Q. So lowercase q is tilde Q, underlined in blue now. and lowercase p is uppercase A. Do you see, now bolded in red, do you see the pattern? I hope you see the pattern. That's the whole point of this exercise. If not, do what you can, and maybe we'll move on. At any rate, I'm going to move on. To complete this next proof, you need to find steps that fit the constructive dilemma pattern. You may also find use for the hypothetical syllogism pattern. The last step in the proof will make use of the redundancy rule. So, you could work backwards. I'm going to suggest, since I've given you enough hints, working forwards is probably not a bad idea. Find steps that fit the constructive dilemma pattern. Constructive dilemma pattern is either P or Q. If P, then R. If Q, then S. Therefore, either R or S. And remember, R, S, and P and Q are here generic symbols for any proposition. And once in a while, R and S might be the same proposition. I think that's what we're going to have here. Or something like that. Maybe it won't be exactly that. It'll be something like that. A or B, that fits the first step of the constructive dilemma pattern. If A, then C, that fits the next step. If B, then D, that fits the next step. So what's the final step? The final step is the one you need to actually type up. And that final step is C or D. Following the pattern, either P or Q. If P, then R, then S, therefore either R or S, where P, Q, R, S are A, B, C, and D. Okay, so that's the constructive dilemma rule on lines 1, 2, and 3. Now here I think the often useful but not infallible mark strategy of ignore lines you've already cited and use the line you've discovered most recently to go where you need to go next is going to work out pretty well. Now let's see. Looks like we do another constructive dilemma here. A slightly different arrangement, C or D, if C then E, if D then E. Now for our application of constructive dilemma, P, Q, R, and S are going to be C, D, E, and E. R and S are going to both stand for E. Remember, R and S are generic propositions, are generic symbols for any proposition. They can stand for anything they need to. In this case, they can stand for the same proposition, proposition E. So C or D, if C then E, if D then E, gives us E or E. That's constructive dilemma on lines 6, 5, and 4. And then you use that redundancy rule to drop out one of those E's. If either E or E, then we can just say simply E. And once again, do not actually cross out any of your steps. I just do it as a quick visualization to indicate what we should be looking at next. If you wanted to do it in hard copy and homework with a very light pencil, maybe that's fine, as long as you don't have a teacher who doesn't like it. But please don't get confused. It's not an infallible rule. Occasionally, you will need to use the same step again. Now, why do I say you may find some use for the hypothetical syllogism pattern? Well, because here's another way of doing the proof. If A, then C. If C, then E. Therefore, if A, then E by hypothetical syllogism on those particular premises, which are lines 2 and 4. And then, since I just used up 2 and 4, I don't think I'm going back to them. My next move is probably going to be hypothetical syllogism on 3 and 5. So let's see what that looks like. B arrow, I'm thinking B arrow E. Now let's check. If B, then D. If D, then E. Therefore, B, then E by hypothetical syllogism on lines 3 and 5. Yep, that's it. That's it. So now I still have to use constructive dilemma, but I'm going to use constructive dilemma on different lines. I'm thinking lines 1, 6 and 7. Let's see if that works. Either A or B. If A, then E. If B, then E. Therefore, E or E, constructive dilemma. Yes, and then we wrap up the proof the same way we did before. Redundancy rule on line 8 gives us our final conclusion. And there you go. That's another way of doing the same proof. Now, here's a nice little proof that requires us to apply one of the patterns available in De Morgan's. I think it's going to be a really simple one. I think we go directly to the conclusion inside De Morgan's on line 1. And I think that's actually all there is to this proof. Let me double check. Tilde, A or B, not the case that both A and B, therefore either not A or not B. If not premise, not both, therefore conclusion, not one or not the other. It works. It works. That's a proper application of De Morgan's. Let's do another De Morgan's. To complete this proof, apply one of the patterns in De Morgan's, and then you have to use a double negation rule to finish the proof. So I'm going to follow my advice here. No working backwards here. Now, I'm not going to follow the advice I normally give, no working backwards. I'm going to follow the advice I typed, which tells me I can do a De Morgan's rules, and there's only one premise. So I'm going to do a De Morgan's on line 1. Applying De Morgan's on line 1, not either, therefore not one and not the other, which means if it's not the case that either C or not D, then it's not the case that C and it's not the case that it's not the case that D. If it's not the case that either C or not D, then it's not the case that C, and it's not the case that not D, which is not D, which has a double negative, which we want to get rid of. So then we just copy and paste and remove those darn tildes. Double negation on line 2. And that's that. Now, practicing conditional proofs. A conditional proof shows that a conditional statement is the case by temporarily assuming its antecedent and showing another consequent follows from it. It can only prove a conditional statement, but once you have that conditional statement, you can derive other types of statement from it. So here is a nice conditional proof. To complete it, assume that the antecedent of the conclusion is true and derive the consequent from it. Then state that the conclusion is true, citing your conditional proof according to the pattern for conditional proof shown in your textbook. Now here I'm going to do, textbook. I don't know if you're using a textbook. Just use the right pattern. The one your logic teacher requires, the one in the textbook, or the one we're doing in this series if that's all you're studying. Okay, so I think we're going to tab. I don't really know how many premises we're going to have here, how many steps of a proof we're going to have here. But let's go ahead and tab over. Oh, darn, it doesn't want me to tab. It's renumbering when I tab is the problem. All right. I can fix this. It's going to be slightly tedious. There we go. I'm going to tab over, i.e. indent. I'm going to indent my conditional proof. Excellent. Now we can begin. So we're going to start by assuming, well, let's read the premises first. If M, then N, if N, then O, if O, then P, if P, then Q, therefore if M, then Q. Now I can see actually how you can do this easily enough with just hypothetical syllogism. 3 hypothetical syllogisms would get you if M, then O, and then if O, if m then o, using those first two, and then using that plus this one if m then p, and then using that plus this one if m then q. But we're going to do it with the CP. So we assume m. We have if m then n, if n then o, if o then p, if p then q. Therefore, if m then q, we're going to assume m, and then we're going to find that q follows from it. Maybe we'll need more steps than just this one, but let's see. I bet we'll need more steps. We're going to need more steps. Anyway, we're going to show that q follows from it, and then we're going to conclude if m then q, by conditional proof on lines 5 through something. We don't know how many lines we'll need yet. So now once we have m in place, and we're trying to get to q, we're trying to get to if m then q by means of this whole conditional proof. So within the proof, we're trying to get from m to q. Now, how am I going to get to q using these premises I have from m? Well, clearly I'm going to go through p, o, and n to get it. So I'm going to work forwards. It's going to be very straightforward proof. Work forwards. The conditional proof at this point will be very straightforward. Work forwards from m to q. And I guess I'm just going to have a simple n, o, and p, and then q steps to my proof. The rest is just details. I'm pretty sure this is what it's going to look like. Let me look over this again before I fill in the details. We're assuming m, and then we're going to do a modus ponens on line 1, which will give us n. If m, then n, and m, therefore n. And then using n in line 2, if n, then o, n, therefore o, we're going to get by modus ponens o. Then using that on line 3, if o, then p, o, therefore p, that'll give us line 8, which applied to line 4 by modus ponens. If p, then q, p, therefore q yields q, and that'll be it. So yes, it's very straightforward. Okay, so modus ponens on lines, the only iffy thing here is citing the right lines, 1 and 5. Now, I'm thinking we're probably going to follow the same pattern. This thing was set out so conveniently. 1, 5, and then 2, 6. Now, if you like, pause, slowly check to see whether this works. Now I'm going to check, maybe slowly, probably not very slowly. If m then n, if m then n, m therefore n by modus ponens on lines 1 and 5, good. If n then o, n therefore o by modus ponens on lines 2 and 6, and now on lines 3 and 7. If o then p, o therefore p, that follows. Modus ponens on lines 4 through 8, if p then q, p therefore q. It's good, we're done, we did it, yay. Now I think this might be our last one. Nope, we have 2 more. To complete this conditional proof, we're going to assume that the antecedent of the consequent is true, same as last time, and we're going to derive the consequent from it. Then we're going to state that the conclusion is true, citing the conditional proof according to the pattern for conditional proof. Okay. No fancy instructions here, just the same thing, maybe a little simpler. Except I have to straighten out the tabs first. I'm going to make a temporary guess that what I'll need is, I'm going to temporary guess I'll need 4 steps in the conditional proof. And then that'll get to my conclusion. So we're going to assume the antecedent of the conclusion, and we're going to show that the consequent follows. Therefore, by conditional proof on that whole assumption and what follows from it, we're going to show that the conclusion is indeed the case. So our premises are A or B, if B then C, if C then D. Therefore, if tilde D then A. And now I'm thinking, did we just do this in the last video? This looks awfully familiar. I think we did this in the last video. So let's do it again. Okay. Oh no, this is not what we did in the last video. This is different. This might be the last one, the one we did in the last video in reverse. Cool. There's going to be a modus ponens, a modus tollens in here. Nifty. I like modus tollens. Okay, if C, then D. Tilde D. Oh, and I forgot to say that's an assumption. If C, then D, and tilde D, therefore tilde C. By modus tollens on lines 3 and 4. And I think we're going to do the same thing. Modus tollens on lines 2 and 5 should give us tilde B. If B, then C, not C, therefore not B. Now, I don't think that's going to get us directly to A, except, oh, it does. By, I'm thinking this is a disjunctive syllogism. Let's make sure. Feels like a disjunctive syllogism on lines 1 and 6. A or B, not B, therefore A. That is totally a disjunctive syllogism on lines 1 and 6. And that tells us that if tilde D, then A, therefore, if tilde D, then A, by conditional proof on lines 4 through 7. We needed those 4 lines of the proof, 4, 5, 6, 7. And we're done. That was it. All right. Now, apparently I've come up with some additional, more complex one. I think I came up with this in 2008, and it's now 2022. So I don't remember when I typed this. To complete this proof, follow the strategy. First, examine the conclusion and see what conditional statement it's equivalent to and by what rule. Second, after you have that conditional statement, write it to the side so you don't forget it. I think in our case, we'll just type it up and just try to remember to fix everything when we're done, like to give a proper number to wherever we type it up. Third, assume that the antecedent of the conditional statement is true and derive the consequent from it. Then state that the conditional statement is true, citing the conditional proof according to the pattern for conditional proof. And then finally, we're going to do that last step, convert it to the desired conclusion. All right, so first step of the instructions typed up here. Again, I recommend you pause and do this for yourself if you can. If you need to, let me rephrase that. If you need to, you should at least try before I give you the answer. But here's the process for those who need it. Pause, try it for yourself, resume. We're going to assume that a particular antecedent is true and show that a particular consequent follows from it, and that will give us I'll use the lowercase custom. Going to assume some particular proposition, P and Q. Sorry, we're going to assume some particular proposition, P, show that some particular other proposition, Q, follows from it. And then state that it follows from it by conditional proof on lines 3 through however many lines we end up with in the conditional proof. And then we're going to somehow convert that to our final conclusion, V or A. It looks like this is the pattern of the proof we're going to work out. This is the strategy. We're going to have some kind of conditional proof, and then it's going to give us by some rule that allows us to convert a conditional proposition to a disjunction. We're going to get the disjunction. So now I interrupted myself a lot. Silly me. First, we should examine the conclusion to see what conditional statement it's equivalent to and by what rule. G or A is equivalent to, I'm thinking the rule is material implication. G or A should be equivalent to not G arrow A. Hang on a second. Let me dig up the equivalent, that particular equivalence rule. All right, here we go. And as the tabs do their best to drive me loony, and heaven knows I don't have far to go. Okay, here's the material implication rule. Tilde P wedge Q means the same thing as P arrow Q. Now, there's going to be some issue with the tildes here. Basically, I'm thinking what's going to happen is this. Still not knowing exactly how many steps we're going to have, but going with these numbers as a basic expectation. We're probably going to do some step that gives us tilde tilde G array, and then we're going to use double negation to get G array out of that. And we're going to get tilde tilde G array by this material implication rule. Material implication tells us P arrow Q means the same as tilde P or Q, where Q is going to stand for A, and P is going to stand for tilde G. In other words, I think this is what's going to happen. I think we are going to get, actually, I can work this into P and Q here. I think we're going to get tilde G arrow A, and then we're going to do a material implication rule on that to give us tilde G wedge A, and then we're going to do it, sorry, I think we're going to get tilde G arrow A, if not G, then A, and then we're going to do a material implication rule to get if not G. I think we're going to use a conditional proof to get if not G, then A, and then we're going to do a material implication rule on that to get not G or A, and then we're going to do a double negation on that to get G or A. Now let me go backwards and make sure this makes sense. G or A does follow from not G or A by double negation, so that's fine. Tilde tilde G or A, does it follow from tilde G arrow A by material implication? Let's see. P arrow Q means the same as tilde P or Q. So we're going to be going forwards. We're left to right. We're going to be going from P arrow Q to tilde P or Q. Change the arrow to a wedge and add a tilde to the antecedent. In this step, are we changing the arrow to a wedge? Yes. Are we adding a tilde to the antecedent? Yes. So this is going to work. This step will totally work. Tilde G arrow A will totally give us tilde tilde G or A by material implication. So now how do we get tilde G or A? That's what our conditional proof is for. So our conditional proof is going to be assume tilde G, therefore, eventually within the scope of the assumption A, therefore, if tilde G, then A, by conditional proof on those lines. So now I'm thinking the rest, finally, if that seemed difficult, the rest is going to be really simple, like absurdly simple. Tilde G is going to be applied wherever it can be applied, and it looks like a simple modus tollens, and that'll give us tilde C. Tilde C will be easily applied by disjunctive syllogism on line 1. So that's it. 2 more steps, and then I'll start at the beginning to make sure everything makes sense. modus tollens on lines 2 and 3 gives us tilde C. And then disjunctive syllogism on lines 1 and 4 gives us A. And that's it. That's the whole proof. It works. Let me straighten out the uniformity of all these things. Okay, so now let's go over the proof from the top and make sure we know what's going on here. Our premises are A or C, and if C, then G. Our conclusion is either G or A. You know what's interesting? I bet we could come up with a totally different approach to this using constructive dilemma. Never mind that. Never mind that. A or C, if C, then G, therefore G or A. We are assuming as part of a conditional proof, not G, because we know that if we can show that A follows from not G, that will give us tilde A arrow G, which we can convert by material implication to G or A plus a double negation rule. And it's not me going through the proof in a way that makes sense. It's easy to follow. What are we doing up here? We're trying to do basics of proving here. So let's try this little exercise again. Our premises are A or C. If C, then G, therefore G or A. So we assume not G, and then we apply some basic rules from our first proofing video, if I remember correctly, to our premises. Not G plus premise 2 by modus tollens gives us not C. If C, then G, not G, therefore not C. Not C gives us by disjunctive syllogism on line 1, A or C, not C, therefore A. Very simple. And that tells us that A follows from our assumption of not G. So we affirm if tilde A, then if tilde G, then A. If not G, then A. That's the conditional proof, not constructed dilemma. Sorry about that typo. This is why I go through it to make sure everything works. I neglected to fill in my citation of which lines here, and I had a horrible typo which cited the wrong rule. That's painful. I sure hope anyone who noticed that earlier saw it fixed now, and is no longer confused, or was never confused to begin with. You might have noticed it's just me doing a stupid typo. Okay, so we assumed tilde G. We found that A follows from it, and then by conditional proof on lines 3 through 5, we affirm if tilde G, then A. And that tells us that either A is true or its antecedent is not true, which is to say tilde G or A by material implication on line 6. And then by a simple double negation step, we can get to our final conclusion. And that's it. That's all. I think we're doing reductio ad absurdum proofs next time. Thanks for watching.